أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم اقرأ باسم ربك الذي خلق خلق الإنسان من علق اقرأ وربك الأكرم الذي علم بالقلم علم الإنسان ما لم يعلم. So today we are going to discuss the section 4 of chapter 16, which is about quality control at AT&T. Oh, before we do that, I want to discuss a little bit about the Poisson distribution, which is something that you all had. So there are a number of files on the Poisson distribution that I will upload to this chapter. I just want to give a very brief introduction. You can look at the details later. Oh yeah, here is the Poisson distribution. So Poisson distribution takes values on integers. It takes values 0, 1, 2, 3, etc. up to infinity, and it can go arbitrarily large. It has a unlimited range, unlike the binomial, which has a finite range, which has a maximum value. There is no maximum value. But of course, on any particular observation, it will always come out to be finite. And so the basic Poisson density is that probability that x equals k is lambda to the k e to the minus lambda over k factorial. Now, if you know that e to the lambda has Taylor series expansion lambda to the 0, which is 1, plus lambda to the 1 over 1 factorial, plus lambda squared over 2 factorial, and so on, then you can easily see that this density will integrate to 1, because it's just the summation is e to the lambda, and you are multiplying by e to the minus lambda, so together they will add to 1. Now here is some of the graphs. If you have lambda equals 1, then the series is monotone declining and the probabilities look like, the second graph with the green curve is lambda equals 4. The third graph is lambda equals 10. Basically, if x is Poisson with parameter lambda, then the expected value of x is equal to lambda. So the larger the lambda, the more, the further away the mean is, the center of the distribution. Now, one thing is that there is the Poisson is a good approximation to the binomial for small values of p and large values of n. So if p is small and n is large, then the Poisson density is well approximated by the binomial density. Now, so in order to understand the Poisson, here are some cases. Suppose I want to find out how many telephone calls will be coming into our and in the olden times there was one switchboard and all calls would be routed from the switchboard. So how many calls are going to come into the switchboard of byte within the next hour? So now the way that this works is that we divide this up into minutes. So there are 60 minutes in the hour. For each minute, what is the probability that a phone call will be received in this minute? This should be low, if under some situation. Or you can subdivide the interval further. You can say, okay, for each second we count the number of phone calls coming in to the second. So as long as when you subdivide, the unit interval is very small, and for each interval, the probability of more than one call is 0. Probability of one call is very low. So let's say it's 0.05, 5% probability of one call coming into PIDE in 1 minute. What's the probability of if one call coming in is, the probability is 5%, what is the probability of two calls coming in? There are two events we are talking about. Event is one call. These are independent events because of the nature of reality, that the different people are calling from different places, so there is no chance that as long as the incoming calls are independent, person X is calling person Y there, everybody who is calling in is an independent factor. So there are two independent events. Each of the events has probability 5%, and so the probability of both of them is the product of the two probabilities. So it's 0.05 times 0.05 is 0.0025, not 2.5. It's 0.03. It's very low, 0.025. So basically, for first order approximation, we can say that there is no probability of two calls. And if the number is even lower, like 0.01, the thing is that when you have a low number, when you square it, it becomes an extremely low number. So the chances are very low. So now we have, so now we can approximate this as a binomial, because each minute is a success or failure. Either one call will come in or 0 calls will come in. One call comes in with 0.5 probability and 0 calls come in with 95% probability. So this is a binomial, and now we have 60 independent binomials. So we add them all up and we get a binomial NP distribution. So that's what and the binomial NP for small values of P and large values of N is approximately Poisson with parameter equal to NP. So it would be 60 times 0.05, which would be 20% of 5% of 1 in 20 of 60. So that's 3. So this would be Poisson with parameter 3. So that's the general pattern. If you have basically, you see, you have a number of events which are all of which are low probability, but any one of them can happen, and they're all independent. So for example, if you have a large crowd of 1,000 people praying in a masjid and they all have mobiles in their pockets, and the chances of the mobile ringing during the namaz is very low for each one of them, then the overall probability will be Poisson, because and it will be fairly high. So and you can calculate how many phone calls will occur. That will be N times P. So you see, so this is a certain kind of setup. Number of soldiers killed by horse kicks each year in a corps in Prussian cavalry. This was studied by somebody. So each one of them is a rare event, but if you have a cavalry, a large number of horses, it will happen. So if you look at that will be Poisson distribution. Number of light bulbs that burn out. In this building we have hundreds of light bulbs. The probability that today one light bulb will burn out is, for each one is very low, but if we take all of them, there will be some probability. So now actually on some days the event will be 0. There will be 0. So this is a Poisson which has a low lambda, and the probability of x equals 0 is relatively high. So that's the nature, and there's lots more material on Poisson, but in the data, and this is a random variable. So today we are studying this. So the number of defects. See, you are doing quality control. This is a real-world engineering example, and this process that we are describing is actually being used. And as I told you last time, one of my students did this for engineering student for his thesis. What you do in quality control is you take a product, you're manufacturing a telephone set, for example, at AT&T. That's one of the projects, and they have lots of other projects. So after the project comes off, you test to see if it has any defects. So it has many different parts, so your quality control department takes it and tests it, you drop it and you bang it and you test the parts and you see how many defects it has. You count the number of defects. You calculate. So normally, because the number of defects is low, presumably you're running a high quality operation. So you take in 100 products and you find out how many of these have defects, where you count defects by some method which we won't go into. And so this number of defects will be a Poisson random variable with some the Poisson lambda t is the expected number of defects in a batch of size 100 or whatever. There is some nt which we are not taking into account here because it doesn't get involved in our calculations. But so we take a batch of 100 products, we test them, we find the number of defects. The number of defects dt is a Poisson random variable with some unknown parameter lambda t. That lambda t is the quality of the production process taking place at that time, which is unknown. Now the observation is a reflection of that, and it is a random variation. It is not the lambda t. The expected value of the number of defects is equal to lambda, but the observed value of the number of defects is not equal to lambda. It's on the average. If you sample many times, the average will converge to lambda by the law of large numbers. But on any one batch, the random fluctuation will be different from the true value. So actually this means that the project could be the underlying quality, and this lambda t keeps changing with time. That's why we keep monitoring. So we are watching and the process as it goes, and if the lambda deviates from the right value, it's never zero. There's always defective probability, but if it becomes too large, then we want to stop and say, okay, you go and examine your production process. Something is wrong. There's too many defects. Now, to stop the process and to examine every part, every aspect of it is an expensive process. So you don't want to just call in a quality control check unnecessarily. So you want to be sure that there is something. So you want to receive an accurate signal about the quality from your quality control process. So there is, I'm following the literature of AT&T. So there is a number which is called ET, that is called the expectancy. This is your tolerance margin. That this is the number of defects that you can tolerate. So, for example, you might be saying that one defect in 1,000 is acceptable. So you examine a batch of 5,000 products, and if there are 5 defects in this, then you are within your expected number of defects. If there are 6, then you are above, and you say that, okay, this is not tolerable. However, if these 6 defects are just the observed value and not the true value, then you don't want to say, okay, go and carry out an examination, because this is just a chance fluctuation. The true underlying quality of the production process is a good one. It's below 5, but by random fluctuation, the number of defects in this particular sample has come out to be 6, which is above your expectancy. So anyway, that's the structure of the problem. Now, how do we solve it? So I've set this up as a historical example that, okay, so a new statistician comes into this factory and he is told that, okay, tell us some procedure by which we should handle the defects. Now, one very simple and naive way, and one very common mistake, is that people take the observation, this is a very common mistake, the observed value, and think that it is the same as the true value. So very common, you can easily trick students who have not taken probability, and many students who have taken probability, and ask them that, okay, I flip a coin 10 times and I observe 5 heads and 5 tails. This means that the probability of heads is 50%. Everybody will say yes, even though this is completely wrong. Has no this is the observed value, and the true value is unknown. It could be 60%, it could be 40%, it could also be 50%. And similarly, you can say that, okay, I take the coin and flip it 10 times and I see 7 heads and 3 tails. It means that the probability is 70% and the coin is not fair. Again, this is completely wrong, but most people will, many people will, because people are not very clear on these issues, even after taking many courses of probability. Even in graduate school, people are quite confused. So you have to keep this, because of this, that's why I'm emphasizing that. You have to keep, in fact, forget about graduate school, this is a mistake which has been made by very advanced and very senior statisticians. The keeping apart the observation and the hidden, unknown reality. And this is actually due to a major philosophical mistake which was made in the Western tradition, in which they denied the existence of the invisibles. In the 20th century, this was done, that invisibles don't exist. And this was part because their enmity to religion, and their decision that we will deny all invisibles, including God. So they made many mistakes, even in science. One of the consequences of this was that they denied the existence of electrons and gravity also, and that led to serious problems in their understanding of science. This is something that I'm covering in my recent essays. Anyway, so one of the consequences, one of the common things that happens is that suppose that there are 2 different treatments of one disease. One of them is very effective, it cures the disease 90% of the time. Other one is very poor, it cures the disease 10% of the time. You can say that one is homeopathic and one is surgery. So suppose that one gives you the nux vomica, and suppose that it happens that the person is cured. So you will say, look, this I did the right thing. Now, you see, one is to judge by the outcome, and the other is to pre-experiment and post-experiment. This is the same thing. Pre-experiment, this is the wrong decision, because you are taking a 10% probability of success and you are dropping the 90% of the success. Suppose that we have 2 people, and one of them is given the homeopathic and the other one is given the surgery option. And suppose that the surgery person dies and the other person survives. So, in both cases, a 10% probability event happened, and the total probability of this is 1%, but it can happen. And it will happen if you do this kind of experiment often. So if you judge by the outcomes, you will say that, look, surgery is wrong and homeopathic is right. If you judge by, so post-experimental measure is wrong, gives the wrong result, and the pre-experimental measure gives the right result. But post-experimental is very visible, so that's what you see. He survived, he died. And the pre-experimental is hypothetical, you don't see it. So even though the pre-experimental is the right measure, it is very common, and this is a kind of mistake which is very hard to, and if somebody makes this mistake, it's very hard to clarify this, because people are, see that, khugare pekare mehsoos thi insan ki nazar. So what you see is, you believe in what you see. You don't check back that okay, this could have gone the wrong way, that somebody takes a very risky move through and drives his car in a very dangerous way, and he survives. He said, look, this is wonderful, even though what he did was very dangerous and he could have gotten killed. But what we do first, as a first approach, what one might do, that okay, let's try to estimate lambda. That's what we're trying to do. Lambda is the unknown parameter, d is the observation. So it turns out that if you study estimation theory, the number of defects is an optimal estimator for lambda. It's also the case in normal theory. If your x is normal, we mean theta variance 1, x is the optimal estimator for theta. So if I want to estimate what is the number of unknowns, I just match it to the observation, which is exactly the mistake that I was telling you. But it's not a mistake as long as you understand that this is an estimator, this is not the true value. An estimator of the true value is different from the true value. So if you see 6 defects, you say that my optimal estimator for the expectancy, the true unknown, is 6. And so that's a reasonable first round parameter. And so you say, okay, that's how I'm going to do. This is our expectancy is 5, and if you have more than 5 defects, then we will say that okay, you do an audit. And there are engineers who are heading various departments, and their projects are continuously being monitored, and so you flag them that there's a black mark, your unit is not performing satisfactorily. Go and check and make sure that it doesn't happen again. So this is a real life situation. So people will come in and complain that look, it just my process is working fine. There's no need to re-examine, and I shouldn't be getting a black mark for not having done my job properly. You just had a random fluctuation. So this kind of complaint comes in. So the statistician who thinks about this and says, oh, about half of these complaints are valid, because if you are just at the border, suppose that you are producing with 5 expectancy, lambda is 5, then how many times will you observe an expectancy in that sample above this? Well, roughly speaking, about half the time it will be above, or half it will be below. So half the time you will be making mistakes in your judgment if you use this rule. So then what you do is you go to the second, more sophisticated method. Okay, you say that okay, the observation is so let's look at the hypothesis test. So first we use the estimation procedure, and that doesn't give good results. So now we use the hypothesis testing. So now it turns out that suppose I want to test lambda t equals et. The null hypothesis that lambda t is less than or equal to expectancy. The alternative hypothesis lambda t is greater than the expectancy. So it turns out that this has a very nice simple structure. The Poisson distribution has this strange property that the expected value and the variance are the same. So the expected value of d is lambda, and the variance of d is also lambda. So the standard deviation is d divided by the square root of lambda. Okay, so there's a misprint here. It shouldn't be dt over et. So we take the observed value dt, subtract the mean under the null hypothesis that the mean is the expectancy. So we subtract dt minus et, and then we divide by the square root of the standard deviation. So it will be dt minus et divided by the square root of dt. or actually dt minus et divided by the square root of et, which would be the under the null hypothesis. So that's we take dt, we subtract the mean, we divide by the SD, though it should be normal 0, 1 approximately. So this is called the, excuse me, yeah.
So et minus dt over et square dt minus et.
I think it should be parentheses dt minus et divided by the square root of et. So this should be approximately normal 0, 1. So this is called the T rate. This is actually, I mean, that's just a statistic. The meaning of the statistic is that this is how far you are from the expectancy in units of standard deviation. So if you have, this is a very common measure in many situations. I mean, suppose we want to grade students. So we have 30 students and all of them have scores. So what we do is we calculate the mean, we calculate the variance, we calculate the standard deviation. Now, the normal score of the student is how far. So if the average is, class average is 80 and one student is 93, then the standard deviation we can calculate, maybe it's 5. So in that case, a score of 93 is 2.6 standard deviations above the mean. So that's automatically an A, because 2 standard deviations above is a very good score. And so basically you can say, okay, within 1 standard deviation of the mean, from the mean to mean plus 1 standard deviation, you give a B. From 1 standard deviation to 2 standard deviations, you give an A. And above that is A plus or something like that. This kind of rule is commonly used to do letter grading, which is relative marking. And that's how relative marking is done. So here we are providing relative marking in the sense that we are taking the deviation from the mean under the null hypothesis that the mean is correct, that is the expectancies, and then we assess. So if it's then we say, okay, if there is a standard deviation is more than 2, that means there is a significant deviation from the mean. So this is not going, this is likely to be something real in the process that's happened. This is the chance of this happening by random chance is very low. It's 2.5% to have a deviation on that size, 2 standard deviations. And so we say that, okay, we reject the null hypothesis that the expectancy is low, and we say that go and we put down a black mark for quality, and we say, okay, go and examine your process and make it better. Notice that here and in all such situations, there is no, and we are saying, okay, there is something wrong, go and fix it, and the engineer will go and he will examine every process and he will clean up the machines and he will, we will never know whether our call was right or wrong, because the basic parameter, the lambda, nobody is unobservable. So there can always be a dispute. The dispute can never be resolved. This is the nature of the invisible, and that is where the empiricists made a mistake. They said that this was the basic logical positivist position, that for any statement you must be able to find you must be able either to provide evidence that it's true, empirical, or that it's false. And if something you cannot judge empirically, then it's non-science. It's meaningless statement. So if I say that there is God, okay, where is the empirical evidence? I want direct empirical evidence, okay, not indirect. So now if we set this sort of criteria that, okay, prove, then nobody will be able to do it. So, but that doesn't mean that there isn't any lambda. There is a lambda, but no, we can't observe it. I can't observe it, the engineer can't observe it, but still we have some clues about what it is, and we have a guess that, okay, if you're deviated more than 2 standard deviations, then something is wrong, go and check. Of course, it's just a guess. Okay, so now this was actually implemented for a while, but there was a new problem that came up. So I'm trying to show you how the learning takes place. So basically, when you have when you're doing this once, it's a very good system that you have only a 2.5% probability of error if the null hypothesis is true. So suppose that we have an honest engineer and he's working very well and his quality is good, then the chances that I will put a black flag on him is only 2.5%. So it will happen only 2.5 times in 100. But now, so for one shot this is true. But now suppose that we are doing this routinely on a daily basis for thousands and thousands of cases. So now what will happen is that in 100 cases or in 200 cases there will be 5 errors. So there are these 5 engineers who are receiving black marks and they haven't done anything wrong actually. So now these people are human beings and they will not like their black mark and they will come in and complain that, look, what has happened? My process is working fine. If you look at my record for the past 5 years, I haven't had a single sample which was below par, and now this just one chance blip happened by chance and you are penalizing me. This is wrong and this is not correct. And this is just a random mistake. It is a flaw of the sampling process. It's not really something that reflects something genuine. So this is certainly seems like a plausible argument. So what people thought about this and said that, okay, this sounds like a reasonable thing. So what we'll do is we will say, okay, between 2 and 3 standard deviations we put down a red flag, but we don't actually call it out. Now if somebody receives red flags in succession 2 or 3 times, then we say, okay, there's something wrong. If there's just one red flag and before it there's nothing and after it there's nothing, then we say that this is okay. So at 3 standard deviations we start to, and then it's not a red flag anymore. So that's now 1 in 1,000 probability of mistake. So that's much better. So so this is a reasonably good system, and with this and with some more ad hoc patches relating to, but this basic system is relatively good, and this was in operation for a long time in Bell. This was actually the quality control system plus a lot of different patches which had to do with special properties of the process. So then this person, Bruce Hoadley, whom I spoke to on the phone to find out about as I was writing this book, because I was trying to find out real world applications of the empirical ways. So he said that, okay, there were 50 years of experience with this. So he said, okay, this system is good, but there are the problems. First of all, there were the system used rules. For example, that if the past 5 periods there has been no red flag and you have 1 red flag, then it will not be considered. In the past 5 periods, if you have 1 red flag, then the second red flag will be considered as a violation, and so on. So there were this rule and many other ad hoc rules. Now these ad hoc rules are not the right thing to do. I mean, what's the reason to look at 5, and even within 5, if it was 5 periods ago, it has a different meaning, and if it was 2 periods ago, it has a different meaning. So that was one problem, that these rules are ad hoc. They don't actually reflect the statistical realities of the situation. The second problem is that now we are doing hypothesis testing. So after we do a hypothesis, we reject the null hypothesis, but we don't know actually what is lambda. We don't have an estimate of the true expectancy. And maybe the lambda is, instead of being 5, it's 5.1, in which case nothing to get worried about. So even though 5.1 is also a violation and 7 is also a violation, but 7 is much more serious than 5.1. So treating them the same is not reasonable. Also, when we reject the null hypothesis at 95% significance level, this doesn't mean that the probability that the null hypothesis is false is 95%. There's a complicated interpretation. So we don't know actually what is the probability associated with the null and the alternative. The Bayesian method works directly to produce probabilities of the hypotheses. So it gives a much clearer idea of what is the true situation. If you have a situation where there is a sharp concentration of the posterior distribution at 5.1, it means that the posterior probability is that almost surely the expectancy is 5.1. On the other hand, if you have very diffuse concentrations, then if you have very diffuse prior, then you say that, well, we don't know very much about what the expectancy is, but it can be in any number between 5 and 7 with 50% probability. So that's a different situation from. So the knowing the posterior probability gives you a lot more information about the hypotheses. So then basically because of this, Hoadley introduced the QMP, the quality measurement plan. This was going to be based on an empirical Bayes estimation of the lambda t. So basically that's the way actually, and now this is currently in use at AT&T. This is the plan that is used to do quality control. So we start by our mathematical model. The number of defects is Poisson with parameter lambda t. Now, just like you have the beta binomial, the normal, so Poisson also has a natural conjugate density, and that's the gamma density. So what we do is we put the we say that the expectancy is gamma dense distributed with some hyperparameters. Now it turns out that it's more convenient to put the prior on E, the expectancy, rather than lambda itself, because lambdas are heterogeneous. Different processes have different expectancies. In some processes you expect very the lambdas are different for different, but the expectancies are more uniform. You want the same number of units to be defective in the same level of quality across different processes, even though the intrinsic physical characteristics of the process determine lambda. E has to do more with the product itself, and so it has a more homogeneous distribution. So we put the prior on E. These are all practical considerations which come up in real world situations as to how to put the prior. So now basically this is the densities. So if E is the expectancy and lambda is the true defect rate, then we have lambda is equal to theta times E. Theta is a new parameter which you introduce. If theta is 1, means that your standard is exactly at the right level. If theta is less than 1, means your expectancy is good. It is your true quality is the true number of defects is less than the expected value. If theta is bigger than 1, then you are in trouble. So basically it's this theta that we are trying to estimate. E is set by the quality control people. Lambda is set by the process. It's the technical parameter which governs the defect rate of the process. Theta is the ratio between lambda and E, and this is what you are trying to estimate as your quality control measure. So our posterior will be coming out on thetas, and so our density is expressed here in the middle. The data distribution is theta times E, which is the lambda, raised to the power of the number of defects divided by number of defects factorial, and times e to the minus lambda, which is theta times E. So that's the data density. Then you multiply by the prior density. Prior density is a gamma density on the theta. Theta is the parameter that you want to estimate. Okay, so then you put them together, you do the rearrangements as usual, and you find that the posterior density of theta is another gamma density, and it is gamma with dt plus d and et plus e. So et is your observed expectancy, which is just the okay, so theta hat ml, the maximum likelihood estimator. What is the ratio of the true lambda to the expectancy? That's the theta. So we replace lambda by its estimator dt, and our maximum likelihood estimator is just the observed number of defects divided by the expected number of defects. So if this is 1, then you are good. If it's less than 1, you are also good. If it's bigger than 1, then you are bad. So that's your theta hat. Mu naught is d over e. This is the prior mean. These are the hyperparameters. D and e are the hyperparameters of the common distribution. So now we are going to shrink this ml towards the common prior. First, we are going to get the common mean of all the defects. So we take all of the defects in all of the processes and average them. We take all of the ratios theta and we average them. See, this theta is something that we can expect to be this is the crucial point. This is very important to understand, that where are we putting our prior. So the lambdas are different. Every process has somebody is manufacturing phone, somebody is manufacturing something else. Their technical specifications are all different. So put a common prior on the lambda would be harmful. I mean, doesn't make sense. E's are also different. We put different expectancies. Different number of defects are expected in different types of processes. Now the ratio, that is the quality. That quality is something that is under control of the engineer. He's trying to make sure that his expectancy is at or below ET. So this theta is what is under control of the engineer, and he's trying to keep it at 1 or below. And so we can expect that across different departments and across different, this theta will have a common distribution, because that reflects the effort of the engineer to try to manage the process. So that's where a common prior would be most sensible. So this is very important, because if you put the common prior in the wrong place where you don't expect homogeneity, then you can get to ridiculous results. So alright, so we put this priors, and then the Bayes estimator, as usual, is in 1632. It's a weighted average of the theta hat, which is the maximum likelihood estimator of expectancy, the quality. Theta is the quality parameter, we can call it the quality parameter. Theta 1 is ideal quality, or not ideal, but the tolerable, the more quality. Higher than is bad quality, lower than is good quality. So we have a prior mu. The prior mu is the observed average of all of the processes. So every process has a quality measure, which is theta, and you average all of them, and you get an average quality over the entire factory. And then you say, okay, we take the observed quality measure and we shrink it towards the overall average, and the shrinkage is going to be based on the observed data variance and the prior variance, and these two are estimated separately, and so we take the weighted average as usual. Now the second step in the empirical base is that we have to calculate what is the prior variance. The data variance is given from the technical specifications of the process. The prior variance is something that is artificial. We have introduced this prior and we have to calculate it. So it turns out, while I was doing this, I didn't know this while I was writing this, and so I did spent a lot of time on finding out the right estimator for the hyperparameter. So there are many different options, and it turned out that the overall results are not sensitive to how you estimate the hyperparameter. So any reasonable method will do. So a method of moments or maximum likelihood, these are the two standard methods, and in this text, in this next chapter, I think I discuss very carefully 2 or 3 different methods. All of them lead to roughly the same result. So a method of moments is simple. You match the moments of the observations to the true parameters. So the expected value of theta is d over e, and that is mu naught. So we've already done that. That's the we know that the average, the expected value of theta hat, the quality control measure, is the mean of the prior distribution. So we just take the sample average, all of the theta hats, and we match it to the prior mean. And similarly, we can take the variance of the observations and match it to the variance of the prior, and that's it. Match the mean and variance, and there are 2 parameters, so there will be some equation, because the variance is not sigma squared anymore. It's something like alpha over alpha plus beta. So we calculate the sample variance of the theta hats over the factory, and we set that equal to alpha over alpha plus beta, where I have given the variance here. Yeah, the variance of a gamma with parameters a and b is a over a plus b squared. So and the mean is a over a plus b. So I set the mean equal to a over a plus b, the variance of the sample of the observed of qualities for all of the different processes. I can calculate the mean, set it equal to a over a plus b, calculate the variance, set it equal to a over a plus b squared, solve for a and b, and I have my empirical Bayes estimator of the hyperparameter. Once I have a and b, then I can get exactly not just the estimator, which is the posterior mean of theta t given dt, that I can get, but also I can actually get the posterior distribution, posterior distribution is a gamma distribution, and the gamma distribution has some elements which are dt and some which are coming from the hyperparameter. So now I have estimates of the hyperparameter, so I know what the posterior distribution is. So with the posterior distribution of theta, I have an exact description of the distribution of theta. So I can look at that and say that this is what the quality is. This is my information about the quality. So if it is very sharply centered around some point, then I have an exact estimate of the quality, that this is between, maybe it's like if 5 is the one, then, and if my distribution is 5.5 with SD equal to 0.5, it's actually a gamma distribution. Gamma can be close to a normal. Then I can say that, okay, this your quality is normally distributed with mean 5.5 and variance equal to 0.5. So it's between 4.5 and 6.5 with 95% probability. So there is some chance, a small chance, that your quality is really below 5. I mean, 4.5 to 5 has some probability. You can actually calculate how much that probability is. As opposed to this, if it is 6, I mean your posterior density is 6 with parameter 0.5, then the region below 5 is only 2.5% probability. So you can calculate actually exactly what is the probability of that this process is out of control. What is given the posterior distribution, you can actually calculate the probability that the lambda, which is unknown, is greater than the expectancy from the posterior distribution. So that is actually the key variable that you want to estimate. So you can use your you can give, unlike all of the situations we have studied, none of them can do this. I can tell to the engineer that the probability that lambda t is less than et is 30%, and the probability that it is bigger, probability your process is out of control, is 70% or 90% or 60%. So in all of these cases, if it's 60% or 70% or 90%, you will be rejecting the null hypothesis, but it's very different situations. And with this probability, then you can make much more accurate decisions. So this was the scheme that was introduced, but it was not introduced just like that without a fight, because there was already a system, and people didn't trust this strange system. I mean, I explained this here over the whole semester. The engineers don't know that much statistics, and this will be many of these calculations will seem quite mysterious. So you say that, okay, what we'll do is we'll run both of these systems together. And so for a while they did that, and so people saw that, okay, the Bayesian system produces reasonable results, but still there were some, it's not, as we said, the results and the reality are different. So post-experimentally, some situations did occur, maybe quite often even, that the empirical Bayes flags engineer as defective when the T-rate system didn't. So he said, oh, this system is bad, even though maybe it's not bad in the sense that based on the results he is saying it's bad, but actually if you go pre-experimentally, then the probability that you will get a wrong evaluation by the T-rate system is high, and the probability that you will get a wrong evaluation by the empirical Bayes system is low. But still this will happen, and if you are doing it thousands of times, there will be people who will say that this new system is very bad. Look, I got this ranked me as wrong. A T-rate system ranked me as right, and I was right. So this system is bad. So such events will happen, and people complain very loudly. So actually, in the end, many compromises were made to win the engineers over to the new system. So the system is not as clean as what I am saying, and this is something that happens in the real world. The clean system is what I've said, but there were many compromises made to match what had been done in the T-rate system, that many exceptions, etc. These were some also incorporated and built into the empirical Bayes system, that okay, we'll go with this unless X, Y, and Z have happened, in which case we will override the empirical Bayes estimate and we'll do something else. So anyway, that's all politics. This is the statistics. Alright, so I think I will end this lecture here, and I will discuss the final exam which people are concerned about. So you don't need to record that.